All right, I'm going to start off with schedule today. Due to my basically, I'm going to be traveling for the next 2 weeks. So this is the last in-person, face-to-face meeting with me for this class. So what does that mean for what we're going to do? Well, basically, the final is going to be very similar to the midterm in that you'll have a programming assignment, which we'll give today. So today, after we're done today, we'll talk about today's programming assignment, and it's down here. I tried to make it more detailed, and I came up with a more detailed. I used pretty much the same rubric last time when I graded your stuff, but I didn't explain it to you beforehand. So I'm going to explain that, but we'll do that in the lab portion of the course because it really is the programming part. Okay. So next week, what's going to happen next week? I'm not going to be here. Well, there's still going to be a discussion. I'm still going to, I guess I can't call it a discussion, but there's still going to be a lecture. I'm going to make it a video. We're going to talk about a few more Python modules that are useful for ArcGIS. And so I'm going to post a video. So that's what will happen next week. But also, and by the way, there won't be any more programming assignments after today's programming assignment, which is the final exam. So next week, just be a presentation. I'll talk about it, demonstrate some things, but there won't be any lab portion of the assignment. All right, so the video will be less than a couple hours. All right. Okay. So you have the take-home written portion. That's going to be posted on Canvas, and that's going to be worth a portion of your final exam score, 40%. Okay. It's open notes, open computers, just like the last one, and most of it will be very similar, and it'll be looking at code snippets and interpreting what is happening. So that is going to go live on Canvas next week, all of that information. And the video will be on Canvas, not on the board, the SBA module part. And as well as, I don't currently have a place for you to turn in the written part. What I'm going to do is make those separate. So if you go to Canvas, I have to be careful when I go to Canvas that I don't accidentally hit other things. Let's see, USM. They don't show grades or whatnot. I think it's pretty easy. I just go to this class and I scroll down. So right now, for final exam materials, I'm going to have another thing under here that has you submit the written part. So we're going to have the written part and the toolbox submission, separate submissions. The reason why I did that is because it seemed like there was a few people that submitted something, but Canvas didn't recognize it correctly. So we're gonna submit those as separate items so that I have both of them. Okay. So I'll add another item here. This one, the code, is basically due on May 3rd, which is the last day of class. However, it's 2 weeks from today. However, the way that I've written it up, and we'll go over this in more detail when we look at the rubric, you're only missing 1 point out of 100 possible points for every day that you turn it in late after that. Okay, so if you turn it in the week after that, so 3 weeks from today, you're still only missing 7 points total. So that's if you turn it in. So it's kind of due May 3rd, but May 10th or 11th is the final drop dead day on that. Now the written portion of the exam, the reason why I kind of tried to separate the two is that the written portion of the exam, which you'll get next week, will be due after that. And I'll actually be back before the written portion of the exam is due. So if there are any questions, you can ask me that. Now, of course, and many people on the coast are familiar with this, if you have problems working on any of the labs, including this one, email me, and I'll still be in email contact and be able to answer questions. All right, so that's the schedule for the rest of the course. Even though I won't be physically present, I'll only be virtually present to help you with the assignment.
Dr. Rayburn?
Yeah.
Are you going to add a spot there for us to turn in our final project? Or do you want
Yes.
to email?
Yeah, I'll add another one. Sorry, I was going to say that. Thanks for reminding me. I'm also going to add a spot on here where the video will be. I'll actually arrange that so that the video shows up before the final exam materials. So yeah, under the final exam materials will be your final project, the final exam code, and the final exam written part. So you have three things to turn in before. Oh, and that's actually what I meant to change, or so thanks for bringing that up. I did change the due date of the final project. That's what I meant for making an offset. So the final project is going to be due May 10th, which is a week from, actually it's more than a week. And I will be back for a lot of, no, it's actually just a week, sorry. Final project is May 10th, and I'll be back this whole week for help on that project. And if you want to turn it into the 11th, you probably can. I'll probably just count a little bit off because I got to get grades in. It might be the 11th. I forgot what day grades are due, but I'll find that out. But the project's due date is May 10th, which is this day right here, and I'll be back this week to help. All right. I'm trying to do here 12. Okay, so let's go over what we're going to go over today. And sorry, what's that? Do you have any questions? Yeah, 3 weeks from today is when everything's due.
Whenever we get to the lab and after we already started the project.
Sure. Yeah. If anybody, I've already looked at a few people's projects. So, and again, for those of you who have questions or haven't even started a final project yet, that's okay. The final project should be similar in effort to a lab assignment. So you're just coming up with an assignment that meets the criteria. It basically uses branching and looping, and you'll be set. All right. I'm going to skip these first two items. These are the things I'm going to talk about next week. So I'll talk about them then. I do want to point out this week that there are a number of modules that come with Python that are useful that we've used. I don't know if you like realize. So okay, one of them is math. You have to import math separately to use it. Right? It comes with Python. There are some other ones that just come with Python. They're actually pretty useful. So I don't know if you realize it or not, but we used one called Random one time. We used one called URLlib. You didn't maybe recognize that one because I wrapped it up inside of its own function. But the one that was called URLlib, you can use it to call a URL and get a response. there's a whole group of modules that that are for interacting with websites and for scraping websites. In other words, getting data from websites. And then there are modules actually for creating your own web server. Okay. Has anybody here set up a web server and run a web server on a computer? No? Okay. So all a web server is a computer that is waiting to receive requests. And those requests come in as text. Okay, it's formatted text, but they come in as a text string. So next week I'm going to talk about Flask, which is a small web server that in Python, once you start it up, your computer is actually waiting for incoming web requests, and Python can be used to respond to those web requests. So you could go to a specific URL, and maybe in the background it ran some GIS operation, whereas if they went to a different URL, it would run a different GIS operation. So they're basically the fundamental building blocks for building websites, and you can do whatever you want with that URL that comes in. When I say URL, everybody knows what I'm talking about, right? We all know. So this is the URL, okay? And that could represent an actual directory structure on the web server, or it could actually be passed into a Python script, and the Python script could return different information depending on what the URL looked like. But this is the computer that's being referenced, and then this is it could be a directory structure, or it could be any other representation of what's out there on that computer. Even a virtual thing, like you could actually run, and you don't want to run a Python script that takes 5 minutes to run. You can only run things that will run fast, but then you could return to the user something. Okay, so I'll demonstrate some of that next week. So this one is called SciHop2. It's actually useful for interfacing Python with databases. Now, when I asked this, you guys have all done a little bit of SQL if you spend any time in the GIS course. So SQL stands for Standard Query Language. Right? So SciComp2 allows you to interface with a database and send SQL statements into a database and basically get records back, and those records are Python lists. So this converts tables into Python lists and back and forth, and so that you can interact with a database in that way. We actually demonstrate a bit of this behavior in the vector course, which is something that we teach next semester. Okay? In its fullness, spatial SQL can duplicate almost anything that our toolbox can do. So you can do spatial joins, you can do intersects, everything that you can do using a toolbox. There's also an SQL statement that you could use, that you could build, that would ask the same question. So that's some of the stuff we cover. Although we don't really couple that with Python too much. But I'll demonstrate this a little bit next week. Today we're going to stick with what we've learned so far in NumPy and build on that, and also talk about SciPy, which, as I said, is NumPy's little friend that does more scientific operations. So there's just a host of any scientific tools that you've maybe learned about in other courses that you've taken. You know, you do different things in math, statistics. That's what we're going to cover. We're going to talk about doing statistics with NumPy arrays today. For the most, that's one of the major topics of today's course, today's discussion. and you can do in SciPy or NumPy or both. And there's a few different data types that we haven't covered yet that we're going to talk about. One of them is what we call a structured array. Okay. All right. Before I get into that, I'm just going to click this link right here. Most of you are Windows users. ArcGIS only runs on Windows, but the GIS world does exist outside of ArcGIS, and probably the biggest alternative is open source stuff. But since Python is open source, it will run, not since, but Python's open source and it runs on multiple platforms. But ArcGIS only runs on Windows. So if you're an ArcGIS user, you're most likely going to be running your software on Windows. So this guy, I don't know how to say his last name, Christoph Volpe. He works at the University of California in Irvine. It's my hometown, actually. That's where I grew up. He maintains a big database of all the Python modules that he knows or uses, and he maintains them for use in Windows. So lots of times, if you're using Linux, you can install different Python modules really easily at the command line. You just type the word pip install, and then you type the name of the module, and it downloads it and installs it. Python comes with Linux. Okay? But with Windows, that's not the case, and so he's maintained this website that builds these. They call them wheel files, and you can install these wheel files. WHELL, like a wheel. You can install these wheel files on your computer to do lots of different things. NumPy doesn't come with Python out of the box, and so it is packaged with ArcGIS. But let's say you wanted to install NumPy on your own, you could do that. Like if you had a fresh computer. So lots of these require NumPy. NumPy is dependent on lots of things, or lots of things depend on NumPy because this is arrays. But you can install just NumPy here, and here they have, the current version and the previous version are usually what they have. Then they usually have a 64-bit version and a 32-bit version. I'm not sure what all these other different versions are, but there's at least 6 versions of every single one. One of the ones that I should have shown there, maybe I'll demonstrate this next week, is I'm just going to hit, is GDAL. GDAL actually stands for the Geospatial Data Abstraction Library. And I used to teach this course up until about 4 years ago. I taught this course using open source software and ArcGIS software hand in hand. So every single example would be in both, but we couldn't cover the same breadth of material, and so I pulled the open source stuff out. But GDAL is a translator for raster geospatial data, and it has a buddy called Ogre. It's not listed there, but it can use vector GIS data. So that's one GIS open source tool, basically that allow you to do things with raster data, warp it, pull it out, put it into an array like we've done before. Rasterio, I'm not sure I'm pronouncing that right, but I've used Rasterio a fair bit. It's one of the things we used to use in the course. It's roughly equivalent to the raster stuff we've been doing so far in the open source world. So it allows you to interact with a raster GIS data source, and it requires GDAL. I don't know why it's called Fiona, but for working with vector data, the tool is called, the module is called Fiona. And then finally, the last one that's very commonly used in the GIS world is Shapely. And Shapely will allow you to do a few different GIS operations with data like buffer, intercept, things like that. Let's see if we can go to Shapely's website. And spell Shapely right. So you can, here we got some buffers, and it's a Python toolkit for doing those sorts of things. Now you're building your geometries differently and utilizing them differently. It still actually will read a shapefile, yeah. So if you're on Linux, you could do this. If you're not on Linux, you have to download the wheel file and install it if you're on Windows. That's how you get a lot of these in. So these aren't installed by default on these computers either. That was another reason why I stopped teaching them in conjunction with each other, because it was hard to maintain at two different websites, two different locations, having to install all the updates with all the open source software and the closed source, the ArcGIS. All right, I don't know what happened to my other data set. My other window. Oh yeah, probably because I clicked on that. So the ones that we're going to demonstrate today, what we're going to talk about, like I said, these two. And then we're also going to talk about Matplotlib. Matplotlib is a powerful library for plotting data, and it's got a website there that you can click on. And it is a bit of a learning curve to be able to take a data set and plot it. It takes some time to be able to learn everything. I'm going to demonstrate a few of them today, but it has all sorts of examples. And almost always, when I want to make a chart, I can find an example of a chart that is close to what I want. And then, once I find the example of the chart that's close to what I want, I can mess around with making sure that the labels are correct and that sort of thing. But it's very useful, and I've used it. I don't even know if this will show up. I should have actually brought these examples. Good. So I've used it, in publications to make charts. So these charts came right out. Like I programmed them in Python. They're basically bar charts, and the bar charts are showing the strength of the connectivity between different areas in that research paper. The next one off. So there's some more bar charts. So these are all the names of different islands, and then this is higher versus lower retention, self-retention. Okay, so if we look at the examples here are the examples. I have a few different examples. I don't necessarily know where I should start, but let's start with the plots. Okay, so I've got a scatter plot and a histogram plot, and the histogram plot is basically a bar chart. The scatter plot is excellent. So I'm going to start with the histogram example there. Okay, so I'm going to click on it and copy it into a new data set, a new And this is very similar. I didn't modify this much I'm copied into IDLE. I didn't modify this much from the example I found in the gallery. So here's a histogram using rectangles. There's some more histograms. I forgot which example I based it off of. Got histograms. Okay. I modified mine a little bit. So I'm going to bring this in here. File, new, file, new file. Actually, yeah. So here it is. And I'm actually just going to save this as C temp SPA, which is the folder I've been working in. I'm going to save this over the histogram example because that's what it is. And then as I change it, I'll change it slightly. Okay, let's look at what it's doing though, first of all. So we're importing NumPy and we're importing this new module that we haven't talked about before called matplotlib. This line is always in a project where you want to create a plot. That line's always there. Import matplotlib.plyplot as PLT. All the examples use as PLT. You could say as plot, but then you wouldn't match the example, so I always do that as PLT. Forgot why I'm using MLab, so let me look down here. It may not even be necessary. I may have taken out that part of the example. Oh yeah. Okay. Yes, it did. But I'll uncomment that later. So this was to pull up a. This was to pull up the to look at the mean and the standard deviations to create a Y. Yeah. In fact, I need to uncomment that. I'm going to uncomment this line. Oh wait, that's the best flip fit line. Oh yeah, I don't need that for him. I don't need to uncomment that. All right. So what this does is it creates a brand new array. What this does is it creates a brand new array with this function, and this function creates a random number, 1,000 random numbers, given this mean and this standard deviation. And it's a normal, random normal. So it creates a nice bell-shaped distribution of data. Okay? Nice bell-shaped distribution of data. And it doesn't use any GIS data. This is just an example. You could use any data. In fact, X doesn't actually have to be an array. It could be any structure. Or any structure. It could be a list or it could be a tuple. But in this case, we're making it a array. Making it a list. Sorry, an array. Okay. So I'm printing it out. Note X is an NumPy array, but it can be a list works just as well. And here I'm building the histogram. And so in the example, it actually asks for the number of bins. What's the number of bins? Anybody take a statistics class before? What are the X and the Y in a histogram? What are the X and the Y? Let's see if there's like a Wikipedia article on it or something. Okay, this is a histogram here. So the X-axis is always just something we're trying to understand. The Y-axis, it's a variable. The Y-axis is always frequency. Something we're trying to understand, frequency. And this has to be a numerical variable. Okay? Numerical variable, frequency. And so this is how many times. So there are more data points right here around, 3 to 5 minutes than there are over 8 minutes. That's the way we can read that. And so we can understand our data better by looking at this and figuring out where most of the values occur in the range. Okay? So this is the range, and This is where most of our values occur. That's what a histogram is. I probably should have started out talking about that. Okay? That's where most of our values are. And one more thing. The bins are the width. The bins have a width. The bins are these things, and they all have a width. These look like they're about 1. So any of the values that fall between this value and this value, this value and this value, and so on. And so you can specify here the number of bins that you want your histogram to be, to have, and here we've specified 50. Okay. So what that does is basically take your range and divides it up into 50 equal portions. This function right here is the function that's doing the work of creating the histogram. So it's plotting your data as a histogram. In fact, it might be helpful to go look at the help for histogram. So we could just type in matplotlib. Matplotlib stands for Math Plot Library. Matplotlib is the name of the module, and we just type in histogram, and it's going to give us the help on here. So these are the parameters that we feed it. So you can actually feed it the bins, or you can feed it the range. Okay, we fed it the bins, the number of bins. All right, there's a bunch of different parameters that we could feed it. Okay, we could feed it whether we want it to be a cumulative histogram, which are not the histograms that we've seen so far. The cumulative histogram will keep building all the way. It'll show you the incremental change. Okay. All right, you can do whether it's a bar or a stacked bar. You can change the orientation, whether it's looking this way or this way. It's kind of conventional to have them face up. Okay. And then you can put the color in. That's what we said, the face color. Let's see if that's on there somewhere. Face color. Oh, maybe it's just called color now. But anyway, we're using an older version, so we've got face color. What does that alpha do? Let's find out. All right, now with almost all of these scientific modules, they return a tuple. In other words, they return a number of different things. So Python, I think we covered this a long time ago, but Python has this multiple assignment feature. So the plot.histogram returns n, which is the number of observations. It returns the bins, which is going to be a list of counts. So it's going to have a number of counts in each bin, and it returns patches, which I'm not sure what that is. Let's see. I'm not spelling patches right. That's why. Silent list of individual patches used to create the histogram. It sounds like something that's useful in some cases, but not always useful. So we didn't actually use that anywhere later. All right, so then it's going to create the plot down here. We can give it labels. I notice I just took this from the example. They had smarts and frequency as the examples. Let's go ahead and change ours. Well, let's run it first. I'm going to run this, and when it runs, that plot.show command actually creates the plot. That's the plot right there. And these are actually randomly generated numbers. Remember, this doesn't actually mean smart. It's not a histogram of IQ. But it's, what was the mean that we gave it?
Yeah.
So we gave it a mean of 10 and a standard deviation of 10. So that's why it's centered around here. It's a normal centered around 10. If we were to change it to 100 and rerun it, you have to close, by the way, you have to close it or you'll get an error, the chart. So now it's centered on 100. Notice that it's still a normal distribution. If we also wanted to change the standard deviation to like 3, we could, and we'd get a tighter distribution. So yeah, we got a tighter distribution there. We could change the colors to blue, and we could run it again and get blue colors. This is the title, the X label, the Y label. So there's not a whole lot of mystery as to what those are doing. If we change those values, we're going to see a different title. Okay? So the mu, the mean, says it's 100, and because I didn't change it down there, yeah, this is actually supposed to be 115, like to match those, but I changed it up there. All right. So let's modify it. Let's say that this was something that I downloaded as an example of a histogram. I want to use it to look at some data. I want to use it to get a histogram of elevation data sets and find out what the elevation looks like in my area, what the distribution of elevation values is for my area. Okay? Or even for all, so let's do it for the whole United States. So to do that, I'm going to download, oops. I didn't mean to open that. I meant to download the data. So if we go back to this guy, and we go back to this week, and we're gonna download the data that I have for this week. This is the same data that you'll use in class. I mean, for the final assignment, this elevation CLIM stands for elevation climate data. So I'm gonna open this up and put it in. I'm going to put it in CTEMP, SBA lab. I'm going to paste it in there. Yeah, just paste it right there. All right, I'll explain the rest of these data sets when we get down to the actual assignment. But let's look at the 2 data sets that I'm going to play with right now. C /temp/HPA lab. Okay, so this is elevation in meters for the United States. I'm not sure if we do take the whole thing. I'm not sure. I'm not sure. We'll find out, but it may be too much data to throw into a histogram, but we'll try it out and see what happens. So that's the USA elevation in meters, and then the other data set that I want to show you right now is just the average June temperature. So, if you look at those, there does seem to be a bit of a inverse relationship between elevation and temperature in June. That's actually, the case, right? You go up, normally as you go up higher, you get a cooler environment. Okay, so I'm going to take the reference to this path, and I'm going to go back to my histogram data.
Which one did you grab the?
The elevation, yep, exactly.
Okay.
Sorry, I meant to go like this. And I'm going to call this elevation path. Now, I want to get the NumPy array that represents all the elevation in meters. We've done that before. We did that last week, right? So here I've created just a dummy array full of random numbers. Okay. Now I want to look at an actual data value. Okay. To look at actual data values, let's do it the same way we did last week. And I think the week before. Didn't we start the week before? No, it was just last week. NumPy array, raster to NumPy array is what we want. Raster to NumPy array. So look at the help for that. And here's the help. Let's just get a sample of it. Raster to NumPy array. We're not going to be worried about transferring it back because we're just creating a histogram for now. So we're going to take our elevation path and feed it in here. And we're going to get our elevation path, and we're going to get an array, and that array is going to be a bunch of numbers that represents all of the elevation in meters for the U.S. and actually a good chunk of Canada and Mexico. All right. So I'm gonna go ahead and save this right now as histo example 2, so that okay. So if I want to change it so that instead of using x here, I want it to not use x anymore. I want it to use array. In other words, I want to delete all this. I'm just going to delete it all right now. Well, I won't delete it all so that I want to delete all of this. So how can I make it so that this is not using x anymore, but it's going to use ARR, it's going to use that array. There's only one thing I need to change.
In the histogram, the data,
Yep. Alternatively, I think I'm going to actually change x up here because it makes a little bit of sense to use x as the x-axis in the histogram. If I wanted to make this a little bit more correct, I can change the x label to elevation. This is going to be frequency. And then I can change this label to just histogram of elevation in the USA. Or I'll just say in NA for North America. So now I'm going to try to run this. I hope it works. Should have thought about this before. But it's just a ton of data. So who knows if it will actually run. Do I have any print statements left? I don't think I do.
Can you go back to the way?
Yeah, that's fine. If it doesn't work, then I wanted to demonstrate subsetting it out anyway. Did anybody else try to run it? It's just a ton of information to feed it. What's that? Oh, you're right. Did mine fail? You do have to import ArcPy. It should have failed. Import ArcPy. Try to run it again. Now it actually like, oh. I get this error I didn't anticipate because I subsetted out the data anyway. But what this is saying right here is that the shape of the array isn't. So x, if I say print, I'm gonna go back and actually call this ARR. Let's say print ARR. If we printed it, it would give us an array. You know, there's a tons of zero values in here. So when I actually wrote this up on my own computer, the first thing I did was take out all the zero values, because the zero values will make a little spike in the histogram, and they're kind of like no data values, right? So let's not count them in the histogram. And at the same time, we could collapse it into a one-dimensional array. Okay? So we used this before, but if we said something like x equals np, or sorry, no, ARR np dot where, we used this before, where ARR equals 0, like that. So what this is doing is saying that in this array, we want only the values where the array is equal. We need two equal signs there in Python. Actually, we need this. Okay. All right. So what we're doing is saying where ARR does not equal 0, we want to keep those values and put them into X. That syntax there will collapse that and just give us those values. I'm going to run it and then switch back over for you. Oops, didn't mean to do that. Okay, so now I've got my histogram. Keep that over there. All right, so we pulled out all the zero values. So just off of 0, we still have a bunch of values. I think this is because I tried running it over and over and over again while keeping this open. That's just saying that the bar chart, something went wrong when we actually created the chart. It's not something to worry about. See now it's gone. I think it's because we tried to create it several times, and so the bar chart maybe partially got created, but it just didn't show. So if I try to run this again right now, I think this is a Windows problem. When I try to run this again right now, I'll get that same error. It's telling me that I already tried to open, and now it killed it. So anyway, if you make sure that you close the bar chart each time, you won't get that error. That's all that error is saying, is that you didn't close up the chart. There we go. So now I'm not getting that error. All right, so the way that you read this, x-axis is elevation, the y-axis is frequency, and so we can see that we have a lot of low areas, and as we get higher and higher, there's less and less areas. It's kind of this weird trend here, where there's a few less areas around 1,000 meters. And the highest value looks like it's somewhere, I don't know exactly what the very highest value is, but it should be somewhere around 5,000 meters, right? In the continental United States, at least, I think 15,000 is about the tallest mountain peak. Anyway, maybe I'm wrong. Yeah, in fact, I mean, if we're really curious about what the maximum value is, we could go like this. I think it's something like print max x. Let's see if that works. No, np Oh. So there's a ton of array functions. Yeah, so that's the maximum value. 4313 is the maximum elevation value to the code.
Dr. Bueller,
Yeah.
where did you find this data if we wanted to, do something similar for other places?
Oh, where did I find this data?
Yeah, where do you get that kind of thing?
Just this data in general, or
Yes, sir.
for this data? Yeah. So this I got from. It's a good. I did it last week, so I had to remember for a second. But what's that website called? It's not the National Elevation Data Set anymore. I should. You get it from the same place you get historical aerial imagery, USGS, same website. Earth Explorer, that's the name of it. Sorry. I got this from Earth Explorer. This is where I got this exact data from. I'm just telling you. And under data sets, digital elevation is there. And this is actually I'm pretty sure this is the GTOPO 30. So in other words, it's 30 arc second GTOPO data. Arc-second elevation. That's where I got it, and you can select, a certain area that you want. If you go to search criteria, and you say use map, and you can yeah, that's what I did. I kind of went like this, and then it downloads when you hit next. Once you have you want the data set you want. It does give it to you in tiles, so it gave it to me in 6 tiles. I downloaded each of the 6 tiles, and I used Mosaic to new raster to get the 6 tiles back into one map. The climate data, I forgot, I can give you the link, 30 arc second climate data. It's also, yep, this is it. All right, so WorldClim produces this. I downloaded the average, the 30-second average, and then I subset it out the same area.
So you want it to be the same cell size? Is that why you wanted the 30 seconds? Or so the tile would be the same size?
The tiles weren't the same size. This actually all comes as a single data set. This does. The other one came tiled, so I had to mosaic it. But this one is, this one's all just one big data set. But yeah, I did it because I wanted roughly the same cell size. The exact cell size didn't matter too much, but I did eventually want the same cell size because I can't do these comparisons between data sets that we'll talk about eventually. You can't do a comparison between the two data sets without the cells being in the same place in each cell. So you need to have the same cell size to do a comparison between 2 data sets.
Okay, thank you.
So I did. I mean, if you want to see, if we zoom in here, I did take these data sets, and you can see how each data set it has the exact same cell size. So how do you think I did that? I mean, that's actually a good question. It's more of a data prep question. It's not really Python. You could replicate it in Python because you can do anything in Python. But how would I get the cell size to not only be the exact same, but the cells to match up exactly? Anybody know how to do that? Because it's a good thing to know if you don't know how to do it. So I'll talk about it real quick. What's that? Yeah. There's some tools to basically the operation is called resampling. But if what you need to do is inside of ArcGIS, if you want to match one data set exactly to another data set, you need to, when you execute the tool, to either, you could just copy the raster. Okay, you can copy the raster, or if copy raster isn't working for you, you could just take a raster and multiply it by 1. Okay, you could do that in ArcGIS. Because if you multiply something by 1, you'll get, why is that something small? Oh, now my toolbox is small. Let me put it over here and see if it gets bigger. All right, good. So if you go under Spatial Analyst Tools, let's say you were going to just copy it by multiplying it. I got to turn it on. I don't know why. Extensions, Spatial Analyst. What you need to do I'm going too fast there. Okay. What you need to do is under Environment Settings, you need to set it's called the Snap Raster. And what setting the Snap Raster does is it makes sure that the corner of your cell sizes match up. So you set Snap Raster. And that will snap one raster to another, but only after you do an operation. So if you don't need to do anything besides copy it, multiply it by 1 or something similar to that, and just set this environment setting, set the snap raster to the data set you want to snap it to, so that it'll match that data set. Now, if you want to match the cell locations and the extent and the cell size, actually, don't ever. When you set snap raster, you always need to also set the cell size at the same time. So set these to the same data sets. And then if you also want to set the extent, change the extent right here under extent. So those should all be the same data set. So
Where was the cell size?
the cell size is under raster analysis. But processing extent allows you to set the snap raster and the extent. So you have to set, for some reason, you have to set snap raster if you want them to line up perfectly. You can't just set the extent. It won't work. You have to set the snap raster. And you can do this in code. You can say arcpy.env.snapraster and set a raster to be the snap raster.
Okay, and so you're multiplying it times 1 so that you're forcing this environment setting into the output raster.
Yeah. You have to do. You can't do any operation. I mean, you can't. It won't change anything unless you do an operation. So you have to do an operation to get the thing to take effect. If I'm trying to match everything, I change all 3 of these. Okay? If you don't set extent, it could be bigger or smaller, but it'll still match. The cells will still match up, but the corner won't be the same. Like if I don't, whoops, that's wrong. No, that's the wrong button. No, that's the wrong button. Okay. It's hard to see the corner on here. You can't really see it because there's no datas, but this is the corner. So if you don't set extent, the corner won't be the same, even though when you zoom in, the cells will still match up if you set snap raster and cell size. Yes, so in order to get them exactly the same shape and cell size, you need to change all three of those. If you want them to be a one-to-one relationship,
You have to multiply the rest of the columns.
you have to do something in order for it to save a new file out. Because environment settings only operates when you actually run something. So lots of times when you download it, like I downloaded it and it was going to be, I was going to mosaic all those data sets into a new data set, right? So I could, when I'm running that mosaic to new data set tool, I could have put those parameters in the environment settings right at that time. But if you don't have anything else to do to it, you have to do something to it to get that new file that's matched to the old file. So you have to run something. I think you might be able to run copy dataset, but I don't think that will work because copy dataset is like copying it in Windows Explorer. It doesn't actually try to recalculate anything. So yeah, you could do anything. You could run a conditional operation where both the true and the false condition were the same. You just have to run something in order to get it to match. All right, so we don't have it up anymore, but we're good. So we ran that. So the next thing I want to do real quick is to demonstrate, because you will actually do this in the final assignment, but and really this isn't rocket science or anything. We've done something very, very similar, okay? But what if I only wanted to get a small portion, like I only wanted some area on here? Well, I've kind of made, let me pull these up in ArcGIS. So I've got CTemp, SPA lab, elevation climate. I've made some of these, so I'm gonna pull all three of these in. Okay, so this is a little sample area that I've made. So what if I only wanted to look at the elevation histogram in that area? I'm like fascinated by this area, let's say, or that's my study area. See right there? That's my study area. By the way, what are these bright spots? It's elevation. Yes. Yep. So the biggest one here is right here. That one. Do you know what this one is? This one's kind of the most famous of the three, probably, even though it's the smallest. That is Mount St. Helens, yeah. So, would this be Hood or Baker? Can't tell. Hood's probably this one right here, because this is the Columbia River Gorge. So I think that's called Baker. I'm not positive, but what are those? All these mountains are former. Well, I don't know if former is the right word, but they're all volcanoes.
Is that what Dante's Peak?
Yeah, this one? I don't know. It might be. All right. So these are all in the northwest, and they go all the way down. There's just a line of them, and you can see they kind of change a little bit. So this right here is another flat top. So that's a lake in the middle of that. In the middle of that one. Yep. Okay. So here, what I'm doing is trying to determine. I'm going to get the histogram just for this area. Okay. So this is similar to something that you're going to do for the last assignment. So it'll be good to have this example. I'm going to call this example 3 here. Save as example 3. So we're going to do a lot this time. What I'm going to do is demonstrate a lot of things, but I'm not going to do. We're not going to work on the actual assignment. So you have to kind of like cobble together the examples for the final. Okay. So here, what we want to do is instead of getting this elevation in meters, we want to first subset that out with the feature data set. And so there is a tool for doing that called let's see what it's called. I forgot what it's called actually off the top of my head. Our toolbox. It's Clip might work, but I wasn't thinking of that. Yeah, extract by mask is what I'm looking for. Do you know where that is? I'll go to geoprocessing window or search. Extract by something. I'm just going to open up. Let's see what the spatial analyst tools, extraction, extract by polygon. That's not right. Yeah, that's it. It's extract by mask is what it's called. So extract by mask takes a raster, you feed it a feature, and you get an output raster. Okay? So let's look at the help for that. And it might work just fine to use Clip, but you have to watch out with Clip because sometimes it will take a raster and return. It'll make the raster bigger. It'll give you the whole raster. It'll just make everything no data except for what you want. So here's the. We need to make sure we check out the extension. Okay. In fact, you could probably copy all this stuff, right? Because we have an elevation data set, and we're trying to mask it. Okay, so I'm gonna copy all that into here. I'll put it down right here. I'm gonna put this stuff up at the top, like there, because that's there. I'm actually just I'm gonna change this to that, and then I'm gonna make my in mask data. I'm just going to copy this down to here. And it's not called mask.shape anymore. What's it called? What did I call it? I gave it to you. Sample 1. And it doesn't need .shape. It needs to look like that. So this should work. All right? So what's this value right here, by the way, when this gets returned? You can go back and look at the help if you want. Or if anybody knows, just say it. What data type is this? This out extract by mask. If it was ArcGIS, if it was a tool, like a vector tool, it would be just a string. It would be a path. But in the raster spatial analyst world, it's not. What is it? What is this? What? Let's go back to the help. Okay, it's always good to know how to read the help here. Okay? Yeah, it's a raster. It's an output raster. So it's actually a raster file already. I mean, it's not a file, it's in memory. And if we want to save it on the disk, we need to save it. But we don't even really need to save it. We don't care about it existing on disk, I don't think, for what we're trying to do. We're trying to see the histogram. So we can take this right here and feed it right into our extract by mask. I'm sorry, no, not extract by mask. Feed it right into the extract by mask, right into our rastered NumPy array because it is a raster. So it's going to here, and now our array, instead of being the entire array, is just going to be the array just for the Pacific Northwest. Okay, just for that polygon. And we still want this line in here because what that does is it takes it from being a two-dimensional array and smashes it down to a one-dimensional array. Even if there aren't any no data values in there, it'll do that. And there actually will be some no data values in there, so it's good to do regardless. In fact, if we were really doing what we talked about last week, we should probably change this to -999 because 0 is going to be a valid number inside of our 0 could be a valid number in our range. I don't know if it will be because of the area I selected. I selected an area that's there might be a 0 though. We might hit somewhere in the Puget Sound up here. It's possible, or maybe down here. But in any case, this way I've removed any possible value. There's not anywhere in the United States that's -9999. It's not anywhere that's below -9999. That's pretty deep. So that's probably best practice. In fact, that'll be better for your example later on because you want to make sure you don't get a 0 value there because you'll be clipping the zeros off. So now I'm going to run this guy. I'll just go right back to here. Does it extract by mask is not defined? Oh, I have to import. Good. Yep, you were going to say it. Import arc.sa as star. Right? Is that the? What's the exact syntax? I gotta open it back up again. Did I kill it? Yep. From, that's right. Okay. Run that guy. Now I might get that error that came up last time that says the one tries to create the histogram. But we'll find out when it actually runs. All right, so now that's the histogram just for that select area. So what I've done is I've subset it out, just that area. If I really wanted to prove it, I could save that extract by mask out, but it works. Those are the elevations. These tallest elevations are like the very tip of Vernier. Okay, I'm gonna close that up. There you go. And you can, an error? What's the error thing?
It says that sample 1 is locked. The error says, this will then,
You shouldn't really actually be utilizing sample 1 for like, it shouldn't matter that it's locked because you're not editing sample 1 at all. You're just extracting.
I think I missed it.
What's your error saying? The tool is not licensed, so you must be missing the one that says checkout extension. Yeah, so it's not finding sample 1. So there's another slash right there. And then it has to go like this. I'm not sure what that means. Just delete that. That's not really a file. Still getting there? You don't have, you didn't set a workspace, so if you just try to do that, it won't work. Yeah. Okay. So, so this. Yeah. Go ahead. Your question.
If we need to do this for the next lab assignment, would you want us just to go into the ArcMap and, create a polygon feature manually and then use that as our cookie cutter, if you will, or our map?
Well,
Or do you want us to strip that?
Yeah. So I'll explain that. Basically, a preview is that these three samples out here. I'll just do it all right. I'll just do it right now. So so for the final lab, you're going to be doing something slightly different. I have the correct. I actually already written a script that does what I want you to do. So I have the correct answers already here. So these are the correct answers for these three sample areas. So here's sample 1, sample 2. Those are the three areas that you have to run it on. And if your data ends up looking like this, then you'll be right. So those are the right answers. Now I haven't yet explained how to get these yet. But what I want you to do is just run it on these three areas. However, if you go look at the assignment, you will get extra points. Go down here. You'll get 4 extra points for allowing the user to define a custom area rather than just a feature file. You still need to be able to feed it in a toolbox. You need to create a tool that allows the user to click a feature class. If you want to find out if you're doing it right, run your tool on the data that I provided, and I have the answer that you need to match. Okay? So I have the answer you need to match for those three. So you can turn it in, and as long as you're getting the right answer, you're going to get full credit. However, you're going to get even more credit if you allow the user to draw on the map an area of their choosing. You're going to get an extra 4 points for that. Okay? So that's that. It'll probably make more sense when I explain what you're gonna do there, and we're not quite to the point where I'm gonna describe that in a minute. All right. Once we get through a few more of the examples. Okay, let me look at the examples here real quick. So I guess the basic answer to your question is, yes, those samples are meant for you to use as you're developing your final project, and you can get some extra points for using your own areas. Okay. All right. So. The second type of chart that I think is really useful to show, and there's tons of different types of charts, but we're gonna limit it to a scatter plot, which is this one, and the histogram, which we already showed. By the way, I do have this mask example. I don't know that we necessarily need to go through with it anymore, but this mask example uses the data from last week, and it's not the same thing as we did before. Okay? But this one, why did I put that one up? I'm trying to remember which side. Oh yeah, this one runs this SciPy binary dilation feature, and it runs a maximum filter. I'll talk about the filters after I talk about the scatter plot real quick. So let's do the scatter example. Probably should have done the filters first and then the scatters, but this is fine. Okay, so I'm going to take this scatter example. I'm actually just going to open this up right from here. So here's the scatter example. Edit with IDLE. This one does a very similar thing. This time though it generates two random arrays and then just sees if these two random arrays are related to each other. Okay, so it's going to generate a scatter plot and also talk about the slope of the relationship between the two lines. All right. Okay, that's fine. You all got that error too? Did you all get this error if you tried to run it? Let me try running it again, see if I get that error. Yep. All right, that's fine that we're getting that error. Which line is it failing on there? Oh, it's inside of Matplotlib. Okay, here it's doing two different things though. Okay, one is it's getting the correlation coefficient. Well, let's start first. First, it's fitting a polynomial, a first order polynomial through the data. Okay, so it's fitting a line through the data, and that line is based on the x and the y information. So let's use Wikipedia one more time. Scatter plot. So we're talking about scatter plots here. Scatter plots help us to establish the relationship between two variables. So instead of what we had before, the x-axis is what we call a predictor variable, and the y-axis is what we call a response variable. Sometimes we call them an independent and a dependent. Okay? So if we're trying to make a mathematical relationship between two variables, which is something that we commonly do in statistics, find a relationship between two variables, we can plot them first and see if there's a relationship. If there is a relationship, they'll be tightly clustered, and they'll either be going this way or they'll be going this way. If they're going this way, there's a negative relationship, negative correlation. If they're going this way, there's a positive relationship between the two values. So negative, positive. In other words, in this case, it's negative. One's decreasing as the other's increasing. So as this one increases, this value decreases. If there's a positive and it's going this way, this one increases as that one increases. All right, let's see if there's another example. There's another example. The durations times the waiting time between eruptions. Well, that's a three-dimensional scatter plot. It's getting crazy. Okay. All right, so if we look at this chart here, it's not surprising that there's no relationship between two randomly generated lists, or in this case, NumPy arrays. So this array was randomly created. This array was randomly created. No relationship. Therefore, the nature of the relationship is like flat. So the slope of that line is 0. Okay. Let's change this up a little bit, and let's just plop in our own silly data. If we just go 1, 2, 3, 4, 5, and then put in 2, 3, 5, 5, 7, 9. I'm still increasing in both cases. I'm going to save this as scatter example 2. And then I'm going to run this. Oh, I see. This end doesn't match up. So I'm going to delete this, and I'm going to delete the colors. And I should be good. So I'm just going to let it choose the default colors. And then run this guy. The scatter example is in the, it's on the, yeah. It's failing now. I'm trying to, I don't think that should be a problem. Okay. X. Oops. Yours worked without it being a float? Let me try it one more time. What did I mess up? It's plotting. B is right there. It is getting to X, Y. XY, there's the correlation coefficient. It's just not getting to that last number. Hold on. I'm just going to uncomment this out and see if the scatter plot itself shows up, because that's the first step. Okay, there's the scatter plot. It's kind of a boring scatter plot. The line itself doesn't show up for me. I guess it shows up for you. The line. Okay. Anybody else's line show up? No. Okay. My computer's been having problems. You get these errors at the bottom that says, okay. Maybe I have to reinstall. I was going to say ArcGIS, but maybe it's just Numpy. Yeah, but my line doesn't even show up. I didn't. Okay, so this line, notice how it's more, if I had more, it's very tightly clustered. You can see a relationship between those two values that I just created. And in fact, this value right here is called the correlation coefficient. And it's a measure of the strength of the relationship. It ranges from 1 all the way to -1, the correlation coefficient. Okay. All right, and this is the slope and the intercept of the regression equation. Okay. The slope and the intercept. So what this says is that for every incremental change in, every 1 incremental change in x, y changes this much. This is the intercept. It's less useful, but it's telling us where that line is going to cross. Where this is going to cross back at 0. All right. So for the final, we're going to calculate a special case of this relationship. It's called the lapse rate. And so, in order not to do the actual assignment, we're going to do a slightly different thing. So one thing is that I created a ton of extra points in here. These are random points. And I did this before class. I created a data set, and then I got the temperature and the elevation, at each of those locations. Anybody have an idea how I did that? Is pretty easy. It's also using that extract toolbox that I think it was Maggie said that. But anyway, I did this extract multi-values to points. So I put the points in, and I put the temperature and the elevation rasters in here, and I got this data set. So what I want to do is I want to see if there's a relationship between temperature and elevation. Because in reality, if I go to, this is real data. If I look at this data set, let's go back up here to the Pacific Northwest. If I look at this data set and I switch back and forth between the June temperature and the elevation, I can see with my own eyes that there is a relationship between temperature and elevation. Okay, as temperature increases, as elevation increases, temperature decreases. See how it's really high right there, and it's really cold right there. In fact, I just thought of this, but I have pictures of my family having a snowball fight right there on Mount Rainier in late May or early June. I think it was, early May or late May or early June, right there. So it snows up there. It's cold, but it's also high. Why does that happen? Well, that's given in the assignment. Talk about that a little bit. So if we go back to the final exam assignment, okay, we're going to calculate this thing called the lapse rate. The lapse rate is water. Basically, the scatter plot has the relationship between the temperature change and the temperature change and the elevation. It's different. The relationship between temperature and elevation changes based on humidity. In humid areas, there's much less change per unit of elevation. In dry areas, the rate of change is higher. The rate of change is related to the slope. So what we're going to do is make a tool for calculating the lapse rate. So in order to do this, you need to calculate the slope and the intercept values, which that's on there. You don't actually have, for this tool, you don't actually have to calculate the correlation coefficient. Well, maybe you do actually. Yes. 2 points for writing the correlation coefficient and the actual lapse rate in the processing window. So you get some extra points for that. So here's the slope. Here's the intercept. Here's the correlation coefficient. We already have that in the code. Okay. All right, so we've got that example. So what I've done here is also provided another example that I'm going to open called, what do they call this? Oh, regress structured array.py. I'm going to open that up. All right. Now, I don't want to get two things confused here. Okay, but there are two different concepts that are introduced on this this particular script. Okay, so the stuff that allows you to read a file is different than the stuff that is looking at the slope and the intercept. So this is getting you the slope and the intercept value, which is already in the other code. So it's basically another way to get it. This is a different, this is a totally different toolbox. But it's still giving, or not toolbox, a totally different library. This is from SciPy. It's giving you the slope and the intercept. You can use this library, or you can use this library here that's using polyfit. That's going to give you the slope and the intercept. However, to get the correlation coefficient, you have to give it polyfit and correlation coefficient. There's two different routines, right? This is a new way of doing it, another way of doing it. So in this module called stats.linregress, stands for linear regression, it returns all of this information in one single command. It returns the slope, the intercept, the R value, which I should tell you is the correlation coefficient. It returns the p-value. That doesn't really concern you for right now, but that's the significance of, if we're testing it for significance. And then the standard error, which also we're not dealing with right now. Okay? All right. So this is another module that will allow you to get the information you need for your particular analysis. Okay? So only this part is really applicable to the final. Only this part right here. So notice that all it cares about is getting two arrays. It just cares about getting two arrays. So you can prepare your arrays in any way you want. So if you want to use this command, you can prepare your arrays using any syntax you want. All right? So now on to the new stuff that is something that I want to teach you, but it's not something for the final. This is not on the final. It's not in the final coding. So don't get confused and try to implement this new stuff, because you don't need to do it for the final project. Okay? But we've already kind of started peaking in the final project, and that's why things are going slightly out of order from the way I envisioned it. But okay, so this is new stuff. So we talked about taking a raster data structure and turning it into an array. ArcGIS also has the ability to take a feature class and turn it into an array, but it's a different type of array. It's called a structured array. And there's a few different ways to think about it, but one of the ways I like to think about it is that it is an array, it is a list, not a list, a dictionary of arrays. It's a dictionary of arrays. And so each array is indexed by a field name. So when you first convert your feature class to an NumPy array, you have to give it the field names you want, and those become the ways to reference it. I think before we run this big old thing, I'm going to create a new file and just run this part right here. And my path is actually different than it was on the machine I was testing on. So I'm going to get the right path. This one can be found under sample points. Sample points. I'm going to copy the path. So I'm just going to get just this information out for now. Okay? Now remember, we're not working with raster data anymore. We're working with feature data. We're working with feature data now, not raster data. And so when we convert this feature class to an NumPy array, we're going to get the fields that we want, and we're going to have, I'm going to print the type of this array, okay? And then I'm also going to print just the elevation values. So I'm going to run this guy, and I'm going to call this just example1.py. There we go. So see what I got was, I got the type, it's still a NumPy array, but it gave me, when I asked for just the elevation data, it gave me just the elevation data. If I want to print the whole thing, it actually prints something that looks like this, and unfortunately it doesn't tell you the name of the fields. But what it's doing is, this is the first observation, the first line. Okay? So this is the OID, the temperature, and the elevation. OID, temperature, elevation. OID, temperature, elevation. So in order to get just the elevation data, I type that. If I wanted just the temperature data, I could type temp, ARR temp. So now I'm asking for just the temperature data, and that's the temperature data. So that's why I say it's like a dictionary, because this is the way you reference items in a dictionary. Remember going way back to dictionaries? So I'm getting out of this array just the elevation data, or just the OID values, or just the temperature values. All right. So now, once I have just the elevation data out, that's when I run this linear regression. I'm going to take us all the way down to here. Okay. I'll leave that up for a few seconds. So now, what I'm doing is I'm running this stats.linear regression model, and I have to feed it two arrays, this array and that array. And when I do so, I get out all these values, the slope, the intercept, the R value, the P value, the standard error. But I'm only really interested in the, well, actually, for the homework, I said the R value, not the R squared value, but here I square it, and I give you the slope and the intercept. The R squared value is actually pretty important. It tells you, anybody know what it tells you? What's the R squared value? If you've taken a statistics course. It tells you the amount of explained variance. So how much your model explains, how powerful your model is at saying slope and intercept are related. I mean, sorry, not slope and intercept. In our case, elevation and temperature. Okay, so I'm going to run this. And actually, I'm going to arrange this so that you guys can still see both. Oops, that's not working. I'm gonna take out these print statements because we don't really need them. Run that again. And then we'll see the results. So these are the results. This is the R squared value. This is the slope. This is the lapse rate. Okay? What this is saying is that for every change of 1 elevation, 1 meter in elevation, temperature is changing this. Well, does it make sense if it's a really small number? Because on average, you move up 1 degree of elevation, you can't feel any difference, right? And so rates are often expressed in, instead of ones or tens or 20s, we express them in a different denominator. Usually, lots of times, it's per 1,000. So if we change this to per 1,000, we've moved this over 1, 2, 3. And we would say, on average, for all the points that we have in the United States, on average, for every 1,000 meters we go up, we're changing in 2 degrees and it's Celsius. So 2 degrees Celsius for every 1,000 meters on average. That's for all of those points that we have so far. You're going to notice when you do this for your smaller areas, which are going to stay vector, they're not raster, so you're not going to run this tool, that you're going to get values that are way different. Well, when I say way different, they're going to be 2 or 3 degrees different in one area than they are in the other area. Okay? Now, think about which one should have more difference. A humid area or non-humid area? The non-humid area, yes, should have more difference. Yeah. Okay, so I forgot which sample it is, but if we go back over to here, let's add them all in. So we have them all. Okay, so you guys could have a hypothesis. So here are the 1, 2, 3 sample areas. Okay, so they're right here. They're right here. They're right here. Which one do you think will have the highest lapse rate? In other words, the most change per 1,000 meters of elevation. Remember, it's the area that's the driest. What's that? It's the area that's the driest. What do you know about the United States? The area that's driest will have the highest lapse rate. So it's this one right here, right? What's this area like? Anybody been out there? Yeah, that's Arizona. If we zoom in here, it doesn't really matter the mountainous. Yeah. So this is like the end of the Grand Canyon area right here. This is Grand Canyon over here, and then we got that area. So it's still out in the desert. We got some high areas. We got some really high areas right here. But we also got some low areas. So yes, that one will have the highest lapse rate. You'll have to find out what the lapse rate is, but that one will have the highest lapse rate. Now, you guys are more familiar probably with areas like this. This is actually the Carolinas area, and this is up there. So which one of these will have the highest lapse rate? You'll have to find out. Okay? Out of those two areas. They're both fairly humid areas, right? Pacific Northwest has lots of Big 12 trees. Lots of paper companies exist up here. Lots of paper companies exist down here because trees grow really well because there's plenty of water to grow them. Okay. So anyway, yeah. So you have to, for the assignment, you'll have to do that. You have to calculate these 3 values. Actually, you don't need to square the value. You do need the slope. The slope is what's really important. Okay, you need the slope. Well, this returns all of these values, but yeah, you're not going to need these 2 values. The p-value or the standard error. You don't even have to use Lin regress. You could use the ones that we ran before. You could use where did I put that? Yeah, you could use polyfit coupled with the correlation coefficient. This one returns the correlation coefficient, which is R, and this returns M and B, the slope and the intercept. So you could use this one and that value. Now, incidentally, so I'm going to go back to my code here. And incidentally, the R value, I'm going to run this again because I don't know where it went. The R value that it ran that it created is pretty small. When you run this for smaller areas, you're going to get a much more significant value. All right, to finish off the structured array stuff, now let's just close this one that I've been working on and go back to this. So this is going to run exactly like. The only thing I'm going to change here is the path because the path changed. So you don't have to type anything in except for change this path. And now, what's going on here? From here up, we've already ran that part. So what's going on from here down is that we're taking the elevation value that we got, that are still in the elevation, we're multiplying it by slope and adding the intercept. So we're going to get an array that's filled with the predicted values using the model. Okay. Right? And then we're going to take those predicted values and subtract minus the actual values. Predicted minus the actual values. And then we're going to save those values out into the temp value. So we're changing the temperature values. Instead of the actual temperature values, we're going to now have the difference between the predicted and the real values. And then finally, we're going to use this function here we're going to join this table that we created back to the original table. So what we'll have is a column that represents all what we call the residuals, the difference between the predicted value and the actual value once it's all said and done. Okay? There's nothing you have to type up there. This is the exact example that's in there. This is the example that's on the page. Okay, I gotta close the table up because I'm trying to write back to the table. I'm just gonna close everything down because that way it'll for sure write to it. All right. So now I'm gonna run it. Hopefully I'll not get an error. All right. So it ran. And then I'm going to plop them all on the map real quick. And what's changed is, if you remember this table beforehand, I used to have just temperature and elevation. Now I have these two new data sets. I didn't replace any of the elevation values, so these are the same. But the main difference is this residual column. It's the difference between the real values and the values predicted by the lapse rate model. And I can actually map those. I'll take the residual values, properties for all symbols. I'm having that. My ArcGIS isn't working great. Properties for selected symbols. Okay. All right. So, unlike the example I showed earlier in my class, you can see that there's a clear difference between what the model predicts and what the actual value is, and there's a pattern to it. As we move further north, we have a tendency to over-predict the lapse rate, and down here we have a tendency to under-predict the lapse rate. That's what these values represent. Okay, and so what this shows is that it'd be better to find the lapse rate for smaller areas because there's a pattern to the data here. That's not what we want. We don't want a pattern in our residuals. All right, now you may be like, what's a residual and that sort of thing. That's okay. Okay, so let's just leave this script, okay, the way it is. You don't have to build on this script, but it is interesting to know that you can do statistical analysis with Python and create a model and look at the results here spatially. Okay. All right, so that's all this script did is find the relationship between elevation and temperature, and then use that relationship to figure out what areas were above and what areas were below the predicted value, and then that's how I made the map.
Did you get the points that show up like that? I know you got them symbolic.
Yeah, well, how did I get them to go that color?
Yeah, I was just trying to like do it.
Yeah, so that's under fields, under value, residual. I chose the residual, and then I had to change the symbology a bit. Okay. All right. Let's go ahead and take a break. I think that what I'm going to do is, I think that I'm cramming a little bit too much in to this lecture. So the other examples where I talk about image processing, I'll push those into the video presentation, and I'll focus more on what we need to build. What we need to build for the script. So, I mean for the final. So I'm gonna go ahead and take our break. I know we went a little bit longer than we usually do before the break, and we'll come back in about 15 minutes and talk about the other items.